Our last example in this lesson is as follows. I want you to imagine that there's a campground where a swimming pool has been built. And the swimming pool has dimensions of 10 meters by 20 meters. So it's a fairly uniform rectangle. The camp owner wants to build a deck around the outside of that pool of uniform width, meaning it's going to be the same width all the way around the top edges, the side edges, and the bottom edges. So it's kind of like a bird's eye view looking down. This particular owner has set aside $1,920 to spend on this deck. Okay, no more, no less. Wants to use that full amount of money. And the decking costs have been calculated to be $30 per square meter. So the question then becomes, what is the widest deck width that can go all the way around this particular pool? Now, because this is a length and width scenario, and length times width is equal to square units, this tells us that there's a quadratic potential here too, because quadratics also have squares in them. So we also need to realize that quadratic equations can be used beyond the capacity of just parabolic ideas. Okay, they can use per square things too. So how are we going to do this? Well, our first step is to figure out what is the area of the decking going to be. Okay, so we need to figure out what are the dimensions of this scenario. I'm going to call this width, and I'm going to call the long one length, if you're okay with that. Just because we usually associate length with being the longer of the two dimensions. So what is the width here? Well, we have the width of the decking right here, which we've called X, on both sides, and we also have the width of the pool, which is 10. So the total width is going to be 10 plus 2x. Okay, the pool and two widths of decking. The length is going to be similar. It is also going to be 20 for the pool, and then there are going to be two widths on either side of it as well. A width here, which we've called x, and a width here, which we've also called x. So it'll be 20 plus 2x. So to find the area of the decking, what we could do is we could do the area of the large rectangle minus the area of the inner rectangle, which is the pool itself. So I'm going to write that in words. So the area of the deck is going to be the area of the large rectangle minus the area of the pool. Okay, so our large one, as we said, length times width will be 20 plus 2x times 10 plus 2x. And the area of the pool will just be 10 by 20. Let's expand this out and collect like terms. So if we use FOIL, we have 200 for the first term. Our outsides will give us 40x. Our insides will give us 20x, and our lasts will give us 4x squared. And then from that, we're going to subtract 10 times 20, 10 times 20, which is 200. So if we start collecting like terms, we're going to notice that the 200s perfectly cancel each other out. We're left with an x squared term. Let's write it first. And then we're left with some x terms that can be collected to give us 60. There we go. So what is the area that she can afford? This owner. Well, she has $1,920 to spend, and if we divide that by the cost of $30 per square meter, that'll tell us how many square meters she can actually afford. Okay, or counting up by 30s, how many square meters could that be? Well, it turns out that she can afford 64 square meters worth of decking. So here's a really cool thing we can do. We see that the area of the deck measures this, and then we also see that she can afford 64 square meters worth of decking. So we can set these equal to each other. So therefore, the actual area of the deck is equal to the area of decking she can afford. All right. If we're going to solve for the roots of this, which we are, let's bring the 64 to the other side and we'll try to factor it. Our first step in factoring and getting this in intercept form is to look for a greatest common factor. And right away that 4 pops out with me. And as it turns out, 60 and 64 are also multiples of 4. So we can take the 4 out and we're left with x squared plus 15x minus 16 equals 0. We can factor this now. We need two numbers that multiply to give negative 16 and add to give positive 15. Can you think of what those two numbers would be? Multiply to give negative 16, add to give 15. Well, 1 and 16 look like they might be good candidates. Since they have to add to give a positive number, how about we let the little guy be the negative number? And there we go. So because there's a 1 in front of here for A, we can go straight into writing the two binomials that when multiplied would give us this trinomial. Because the only way to get 1x squared is to have x times x. We can put negative 1 in here, and we can put plus 16 in here. Now, in order for the left-hand side to equal 0, well, 4 isn't going to change, it's a constant, but if this were equal to 0, 4 times 0 right away makes this side 0, and it doesn't matter what this is. In a similar fashion, if this term is 0 and it gets multiplied by anything else, the whole left side is going to be 0. So from here I can say x minus 1 is 0 and x minus 16 is 0. Or sorry, plus 16, there we go. If I solve for x, or for the roots, I get x is 1 and x is negative 16. So in this particular problem, which one of these answers makes more sense? Let's go back up to our diagram. Is it possible for me to have a width around this pool that is negative 16 meters? I don't think so. Negative 16 meters would be actually cutting into the pool and making the pool smaller. So this root doesn't make sense in the context of this question. It doesn't mean it isn't an answer, it is, but we're going to be working this time with the positive root, x equals 1. So does it make sense to have a 1 meter width all the way around? And the answer is yes, it does. So therefore, the widest that the deck can be is 1 meter all the way around. That's what she can afford to build. As always, if you have any questions with the problems that you're going to try, give me a shout. Do take the time to work through some problems and have these examples handy as you do so.